Before we start creating objects, let us expand on our knowledge on how to organize our project. In the next section, we will learn how to create our own class, our own type of object, but before we go there, let us learn how to create our own functions, our own methods, and save them in a separate file. In this way, you can have the sense of creating your own library of functions that you can use whenever you want. And it won't be just a sense, you will actually be doing that. And later on, when you are more experienced, you will be able to save all your functions and classes into an actual library file, a DLL, what a Rhino plugin basically is. And then you can use them in your projects. That's one of the coolest things about programming. Everything gets built on top of the previous work, and most of the things you write can be reusable, which enables an enormous acceleration of progress in your own work, but also in the general world of programming, because all the software that we see today is so cool and so complex because it was built on the platforms of previously developed and tested routines. If some of you watch the C++ lessons or know how to program in C++, you realize that in C++ it is possible to have functions outside of classes. You simply create some functions and include the file where they are, and then you will be able to access them. In C#, if we want to create separate functions, we will have to put them in some class. So what we will do now is simply create a new class called useful functions. So let's right click on our project. We will create this file in the project root, so to speak. And I will not add the class here. We can go to the actual class view that we can use for this, and then right click and add a new class. That would be more convenient. It's very simple. As you can see, Visual Studio will ask you to choose type of class. This is the most standard class, .NET 1. With the CS extension, we will name it, as we said, useful functions. And we will store our functions here. So let's edit. Go back to our Solution Explorer. And as you will see, Visual Studio created a new CS file. It put it in the namespace. That's the same for the entire plugin. And it created a new class with this name, nothing else. And in this case, we actually don't need to do anything else. We just want to add some methods to it, some functions. If you feel the need now to brush up on the subject of functions, you can. Again, check my C# classes, check it online. First, what we will do is add some of the standard Rhino namespaces that we will definitely use. So I will add a couple of them right off the bat. The Rhino one. We will most definitely use the Rhino commands one and Rhino geometry, and very, very probably some collections and input, but we will see that along the way. And let's immediately start by adding a method or a function. And if you learned how to do it, it's very simple. We will add some identifiers here that I will talk about in a minute. And we will call our function drawPoint. And just for the sake of exercise, drawPoint, I will add some parameters to this function. One is of type line, called line, and one is a boolean called start, which I will explain right away. Why did I imagine the function like this? It's nothing obligatory, it's just pure my imagination. So let's dissect what's going on here, and then we will expand this. So first, this is the syntax for writing a function, or a method as it is called when it's a part of a class. And in C# or .NET environment, functions will kind of always be a part of a class. This is an access modifier. This means that this method can be accessed from anywhere. When you put your variables inside your class, fields, properties, methods, you can set them to be private, protected, internal, internal, and public. So I talk about this in my C# basics lessons, and I'm not going to repeat it here in completely, but private means that it can be accessed only within the class. Protected versions can be accessed from the class and other classes that inherit from it. Internal, for example, means that the methods and properties can be accessed only from the current project, because as I told you, you have solution and multiple projects. And public can be accessed from everywhere, which is exactly what we want. Now I will shortly just explain what static means for you. And I'm sorry for those of you again who find this slow, but I like to be thorough. I like to explain everything to you so that you can actually understand it and apply it later in practice. I'm not about flashy examples and flying to some functions and classes where you can just repeat what I wrote and then not understand anything at all. So if you want to understand why our function in this case is static, if you do not have much experience with object-oriented programming, you might not fully comprehend what that means. And if that is the case, don't worry. It's not important to understand fully what a static function means, a static method means. And you could take it for granted until at one point it will be clear why some methods or fields or a class might be static. But let me give it a shot. If you watched my video in C# Basics where I explain classes, you know that we usually create an object of a specific class. We will just write point 3D, right? Point 1 is point 3D called the constructor. And then we can do this for multiple points, point 1, 2, 3. Each point will have its own coordinates and everything, all the properties, all the fields inside of this function can be unique for that one. But if I declare something to be static, then it will be the same for all objects of that class. Imagine if I had a static field inside point 3 called a string name, static string name equals p. Imagine if this was a part of this point 3D class. Now every point I created will have one single value, and I don't mean the same value repeated, I mean one value stored only once in the memory. Now the cool thing also is, with these static methods, you do not need to create an object of the class. Later, when we use these static functions, we can just access them by simply writing useful functions, as you will see, and we will access this function with the dot operator. So we do not have to actually instantiate this class with a new word and so on, which is very useful. So in order to demonstrate all this, let's create a new command, how we used to do, with a new add item, empty rhinoceros command, and we will call it x divide curve. And it will be a secret what this command will do until we actually do it. And inside this command of ours, let's create a new line like this. Of course, let's go to one of our previous commands and add all, just copy paste all of these. I'm not sure if we're going to use them all now, but you can optimize the code on your own. I will create a new line, and this is how I will do it. I will truncate the code a bit. You're not a beginner anymore, so you can try to optimize your code to have it in less lines. I will create a line from 2 3D points, and I will instantiate them immediately inside this constructor, so kind of a nested constructors. So new point 3D with the coordinate 0, 0, 0, and another point with coordinates 10, 0, 0, and a line will be created between those 2 points. So now what I can do is call my useful functions, and because we have a static method, I do not have to instantiate it, create an object of it. I can simply access with the dot operator my function, and I can pass it a line, and I can pass it some bool parameter as true. And this is enough. Now remember that our function is empty at the moment. It doesn't do anything. So let's put some code inside. I can simply right click here and say go to definition, and it will take us right to our function. Now we learned that we need a Rhino document to draw something, right? So inside this class we do not have our Rhino document. So theoretically I could not draw a point here. So we would have to pass it from our command. But let's leave that for one of the next videos and one of the next lessons. Let our function now just return the point we want, and then we will draw it in the command. So what we will need to do is we will need to exchange the return of the function, and now we want it to return point 3D. And now our function actually has to return something. It cannot be empty. That's why probably exactly it says not all code paths return a value. Now we have to return a 3D point. So let's do it. Let's change it. Let's create a 3D point and call it a result point. Instantiate it as new one, and then we'll say if the user passed start, so if the user passed true for start, we will simply return the start point of the line. How do we access it? Well, if you remember, our line has a property called from, which is exactly the start point. If we passed false, then our result point, let me copy this here and here and here, will equal line 2. And what we will do is simply then return our result point. And that is our very simple function. And this is how our command could look now. Let's go to our command file, divide curve. Because we know that this function now returns a point 3D, we can write this, point 3D, line point equal this. Of course, if you want, you can write var here and use the implicit type. It will be the same thing. I just come from the C++ world and I like this explicitly, strongly typed types. So what we can do here as an exercise, we can now access our objects table and we can add this line that we created here, and we can add our point. And of course, we can access our views and redraw them. Now, if you pass true here, what Rhino will do for you is draw a line and point at the start. If you passed false, it will draw a line and point at the end. You can build this, test it. I will speed this up just to show you that it works. So X, divide curve, and here is our line and the point at the start. If you passed false as an argument, you will get the point drawn here. Congratulations, you created your first independent function that does a little routine. Now we will continue creating functions, or methods as they're called, inside our useful functions class, and we will use them to draw our objects. Curve parameters are very important, so let us add something else to this example. Let us read the curve parameters, and then we will use those parameters to read what the tangent value of the curve is, and then actually draw them. So let's first create an array that will save those parameters and create a function that will draw tangents. Now I just want to show you, to push it a little bit more, just to show you some additional functions that you can do. If you hover over this method, you will see that the peculiar thing is that this method actually returns an array of double numbers. So what could be an array of double numbers? So you can go and check this out in the help file. I will not go back and forth anymore to do it for you. You know how to do it right now. And I will simply create an array of double numbers that will hold whatever this function returns, and because I know what it returns, I will call it parameters. For every single point that will be on the line, every single division point, it will be simple. It will be a domain on the curve, a parameter on the curve. And we talked a little bit about domains before, and I'm preparing separate courses on Nurbs geometry, so you can check those out. But you learned before, and I hope you understood that every point on a Nurbs surface or a Nurbs curve has a single double precision value, which is called a domain. And let us use these domains now to create something interesting. Let's first create a function, and then we will talk about it. We can simply copy this. You can do this very often. And I will call my functions x draw curve tangents. Tangents? Yes, tangents. Again, it's a secret what this function will do, but not anymore. Will draw tangents at specific curve points. So let's think of what will we need for this. Well, let's use this nice double array of, remember, angle brackets, an array of parameters. Let's pass a curve to this function. We're not passing these points to draw now, we're actually passing a single curve to this function with its parameters, and we will pass the Rhino document so that we can access it and we can actually draw inside of it. Now what we will want to do is we will want to iterate not through some points, we will want to iterate through these parameters. And we will delete this and open some curly brackets because we will want to do multiple functions, multiple things inside here. So what will I want to do inside here? Well, first of all, for this particular current parameter, I would like to get a point, a 3D point at that domain. I will use my curve that I passed, I will use its point at method, and I will simply pass my current parameter using the angle brackets to access the element of the array, right? Now I can use that parameter to get a tangent to that specific tangent at that particular point, and a tangent is nothing than a vector, right? A vector that will be always returned in a unitized form. So I will call it tangent, and I will use the method that the curve has that's surprisingly called tangent at, and again I will pass my domain value. Great, now we have the point at the specific spot, we have the vector at the specific spot, and since our tangent is unitized, we can draw a line we can create a new one that starts at our point and ends at our point plus tangent, but again, since our vector is unitized, as I told you before, you can actually multiply it by some number. So in this case, if we are working with meters, in meters, we will actually draw a line that is 10 meters long. Hope you understand this. Then we will simply draw those lines. Again, Rhino document is where everything is saved. A Rhino document has something called an objects table, where all objects in the document are listed. You can access them here to replace them, delete them, swap them, and what we want to do now is just add another one, another object, using our tangent line geometry. Except we will add a line, not just add for an object, right? And then we will redraw the view. So we can go back to our divide curve command, and we can use our static functions called draw curve tangents. We will pass our parameters array. We will pass our curve. Which curve is it? It's the current curve that we are looking at the moment in this particular iteration, and we will pass the document. So let's see if it builds. Let's test our command. I will speed this up just to show you that it works. I just drew some 3 random curves here. I will call xDivide curve, select them, and as you will see, my first function will draw the points. My second function will take those points and find what the tangent is, and as you can see, the length is exactly 10 meters. It will draw tangents outside of these points. Great. Now let's continue and create some curves, lines, polylines from scratch. So you learned how to divide the curve, how to draw points, work with a normal type of array or list, and I hope you understand the curve domain and parameters. I talk a lot about it in different videos, and you should either learn about it online or watch my Nurbs lessons if they're already out. All Nurbs surfaces and curves have domains, their own parametric space, and by using those parameters you can access any point on the curve, and as we will soon see, you can access any point on a surface. Now let's go and create some curves. Now we will start creating geometry, and you will get introduced to different functions and methods on the way. Since there is so many of them, you will always have to try to understand how they are used so that you can go to Rhino SDK help file and use other methods in the same way. And I was pampering you a bit so far, but you're not a toddler anymore, so I will switch into the second gear. We will select some curves and divide them automatically into a number of points, and we will draw all these points. So in this exercise you will learn how to use the curves you selected in the xCurve selector function, pass them to a function that will divide them, and then pass them to a different function that will draw them. It's a bit of a leap in terms of complexity, but we can do it. It's nothing scary. Now, in our command, which was basically only done for testing, let us delete everything for the except for the Rhino, for the return of the result success. And let's start by defining some variables that we will need for, okay, I'll tell you the secret now. This command will take a curve in and divide it in some parts, similarly to the divide command that you have in Rhino already. But this one you can automate and use it as a part of a bigger process. So let us save some curves that the user will select. And we will use again this curve list that we used before. Again, you can use any type of array, Rhino list, whatever you like, but why not use something that's specialized to hold a list of curves, an array of curves. We will define some divide number, let's say 10, and you saw before that we actually prompted the user to enter some number in one of the last videos, and you can as an exercise later on prompt the user to give you a number. Right now I will give a fixed number for the number of divisions that we will use on our curves. Now we will create some 3D point array. This array will hold all the division points for every curve, and you will see that this is not strictly necessary to have this array, but I will put it now just so that we can exercise a little bit of cleaning and refilling the array. I want to show you how to do that. Let's call it a div point array. I guess we could instantiate it right away. If you do not see any of this, do not forget to add Rhino collections for these lists. Now we would like to select some curves. Since we do not have a separate function to select curves yet, why don't we just copy the code you have from your curve selector? Where is it? Yes. Here is the code. Of course, we don't need all of these things, so we will just copy the code until here, until we actually enter the loop. All these things we don't need, so I will delete them, and I will show you how to do this. Very, very often you will just need to copy codes, pieces of code like this. Remember, this was counting the types of curves we needed. We don't need that anymore. We experimented with different arrays. We don't need anymore. And this is what we need. We need a new object of get object, set the command prompt, geometry filter, get multiple ones. And right here at this moment, we have a curve array. Just if you want to be 100% sure, you can check the count of our curves array. What you will usually want to do something like this, and you can say if the count is smaller than 1, which means it's 0, you will simply return failure, because you do not want to continue your function if you do not have any curves in the array. So if you find yourself here at this moment of your command, you have an array of curves that has at least one curve selected, and you will want to divide it. So let's comment this a little bit. Let's say this is step 1, select curves, right? And you can indent this just a little bit. Then we can say that the step 2 should be divide curves. And because we're trying to introduce something new every time, to expand a little bit on our knowledge every time, let's add another check here before we actually add the curve to our array. Let's check if we didn't by accident select one of those very, very short curves. You will see when you work in Rhino, sometimes it will happen to you when you use different processors that you generate extremely short curves, like the curves that have a length of 0.000001, and you don't usually notice them, and sometimes that they can screw up your code or your files. So for example, you can check here if the curve exists, but it's not enough that it exists. We also want to check if curves is not, remember the not operator, is curve is not short. And then Rhino will want to know what does short mean, and we'll say, well, how short? we will access Rhino Math class and some of its variables, that one of them is called zero tolerance. Let's not dwell on this right now. This is how you basically check if the curve is too short. You will see you have some overloads, but the point is that you put the tolerance. You can actually, if you want, you can put here 0.001, let's say, if you're working in meters, so every curve shorter than 1 millimeter will be selected or something like that. So when we did this check, let's divide the curves. We will enter a loop, of course, and as we learned before here, why not delete this var here and make a variable at the top of the command once that we will use as a global iterator. And now what we want to do is iterate, of course, through all the selected curves. And I'm sorry, I've almost forgot to tell you, we do not want a double array here. What I did is I created an array for selected curves and then used one that was copied. We don't want that. We want our array of selected curves to be filled in here and to be dealt with here. We only want one array. You don't want to make the mistake I did. But I told you before, I really like making mistakes like this, just to show you how to recognize the mistakes in your code, and this will happen to you a lot. So we will go through all our selected curves. We will use the count to know how many times we iterate through them, and we will open the curly brackets. Let's indent here this a little bit. When we access the current curve that has been iterated to, if I were in C++, I would kind of have to write 20 lines here probably, but luckily we're in C#, and I can access the curves methods with the dot, and there is a nice method that says divide by count. And you can check in your help file what parameters it takes, but it takes the segment count, for which we have our division number, right, defined as 10 there, and we have something that's asking us to include ends of the curve. Yes, we can say we want to include ends. This is your choice. And what we will have is an out parameter, as in, if you remember, if you have an out parameter, it's something that has to be filled inside the function and will be filled inside the function, and you will want to pass our div point array. Now, remember when I told you that this is not strictly necessary? Well, it's not strictly necessary because you saw that there is an overload here that doesn't return the array, but we want them. And you will see that this is underlined here. Why? Because it's an out variable, and with the out variable, out parameter, you cannot forget out. Well, apparently this was not the only reason. Why? What's the second reason? Let's see. The second reason is that obviously our type doesn't fit, right? We wrote .3D list here, but here, as you can see, it returns a .3D with angle brackets, which is a very standard array in .NET. It's not a list or anything like that. It's the most standard array. So what we can do is use the simplest solution, create a very standard div point array, and we will not instantiate it. We will just, we will just write this. And in my C# basics lessons where I talk about arrays, you can see this is the most standard type of array that you can have in programming. And now, as you can see, we solved this both just to prove it to you that if I deleted out, this will still be underlined. So out and the type were both problematic with this variable. So for every selected curve, we simply divided it and then got the point array. Why not use our useful function to draw points, right? But as you see, we have a draw point, a single point function, right? Doesn't really fit, and we're kind of passing lines. So why don't we go fast here and make another function that will draw points? And what you will want to do every time, what I don't do here because I want to speed things up, is the following. First of all, this function can be void. We will call it draw points, and we will pass it the point array the one that we just got there. We'll use the same type, call it point, and I will pass the Rhino document of the Rhino doc class. I will explain this in a minute. And the thing I said you shouldn't forget is to comment it. If you type 3 slashes, you will have this comment XML one that will appear in the descriptions in the IntelliSense, and when you hover over your function, and you will want to write this method takes a point array and draws points. Just to show it to you, this function is now empty, it returns nothing, but if you go to our useful functions and you find it, there it is, draw points, and you pass our div point array, and you pass the Rhino document that we have here, it is passed to our command anyway. And if I hover over it, you will see that this method takes a point array and draws points, exactly the comment that I wrote here. So this will be a very, very simple method. We will just iterate through all of the points that we got. You will have to notice this slight difference. This is a standard array, and it doesn't have a property count. It actually has a method count with the open and close bracket that will give you the number of elements in the array. We will use our Rhino document, access its object table, and add our point. Which point? Well, the point we are currently iterating through. And let's say after we are done, we can also call the redraw. We already called this function from our command, and theoretically this works already. So let's build solution and test if we can actually draw a couple of curves, select them, and see if they get divided in 10 parts. We don't need the plugin manager because we already used this function, this command before. We already installed it. Let me draw a couple of curves here. And now if I press X divide curve, select some curves, you will see that every curve will be divided in 10 parts and all the points will be drawn. Let's just continue the next video a little bit more and see what else we can do with this. Now this was a fairly simple example of drawing points. You already learned at the very beginning that you can add objects to the object table with the doc objects add methods. So I just wanted to give you something extra and show you how to divide the curve. Let's continue, let's go on a function spree. Let's create some functions that will be as useful as this one, so that we can play around with it a bit. Let's create another one that draws lines from points. And of course, you're free to test this function with passing false as a parameter and see what comes up. So let's just add another one that will simply draw lines from points. We will pass the same thing, except we will not pass this true. Function create, let's say, lines from points, and we will not have all this complication. We can delete everything, and we will simply iterate through all of the points. And in every iteration, we will create a line starting with the current point and ending with the point that is at the next position, so e plus 1. Be very careful here, you do not want to make this mistake. Once you come to the last point and you call this, it will call a non-existing element of the array, because there is no point after the last. So you have to stop at the count -1 here, just so that you can access the last one on the way. If this line is not null and this line is valid, we will simply add this line to our document, as we learned how to do. And of course, we can redraw our view here. Very nice. So just for the sake of testing, we will add this function here. Lines from points, we will pass it the points, we will pass it the dock. Very nice. And let's, just for the sake of fun, let's call this function again. Now passing false to see if it works, to see if drawing of a curve using these points as control points works. And let's finish with the polyline. Polyline is very simple because guess what? Its constructor can just take point array and make a polyline. So if you want to have a closed polyline, the first and the last point will have to be the same. So without further talking, let's fast create another function. Let's copy the line one. We're doing this really fast now to create polyline, create a polyline from points, and we'll call it X polyline from points. We're passing the exact same thing, except now we actually do not have to enter into any for loop. We will create a new polyline that, if you scroll to the overloads of your constructor, you will see that it actually takes a 3D point collection. We will just simply pass it the points. And if you want the polyline to be closed, for example, all you need to do is just add the first element of your polyline to the end. So this will close the polyline, right? And then you can just simply copy this check. If the polyline is not null and the polyline is valid, we will add it. And you can actually use the add polyline method. That's also nice in the C#. They have an add method for every single geometry type, and you want to redraw your views. And finally, let's draw a polyline as well by passing it points and dock. Very nice command we created here, where we select some points and we use them to draw different types of lines. So let's test it fastly. I will create some points here. Now I will call my create curve from points, select them, and you see we have a lot going on. We have one curve, the first one that's created through our points. We have one that is where we pass the argument false, that created using these points as control points. If you press F10, you will actually see, let me just hide this for a moment to show you what I'm talking about. So this, you can see if you select the curve, these are its control points, which are our original points that are taken as an input. Then we have this, those are the two first functions. Then we have lines from points, which basically went from point 0 to point 1, created a line. Then from point 1 to point 2, created a line, and so on. And then at the end, we had our polyline from points, which is this one, which started here, went all the way here, and we closed it at the end. And as I told you before, you have to keep an eye on the order of points. Once I called my function, when I selected them all, the order of drawing was important. But what if I select my points in a different order now, one by one? You will see that that will now be the order of points used for the curve creation, and that's something you have to keep in mind when you create code. So let's stay a little bit more on curves and see how to create arcs and circles, and use a little bit of random numbers for that. You saw how easy it was to draw points, and the best thing is that you have a function now that reads points from an array and draws them. So now every time you have a point array and you need to draw them, you can simply call that function, pass it the array, and you're done. You're already building your own library. Since we will do a lot of selections, it makes sense to have a function that selects different geometry as well, don't you think? So let's make a function that selects points for us, and we can use that in these lessons to create different curves, lines, and polylines. let's create a useful function called select points. Let's do it from scratch as an exercise. We want a public one, we want a static one. It can be void, it doesn't have to return anything, and we will want to select points. So what will we pass as a parameter? We can pass some message, and we can fill out a point 3D list array inside. Let's call it points. We do not need a document because we will not draw anything or add anything to the documents table or read from it. That's good. So what problems do we have here? This is not recognized. Of course, we will need the collections namespace in order to recognize our collections, our list and arrays. And why is this underlined? Because we have an out variable here, and if you hover, it will tell you the out parameter points must be assigned before control leaves the current method. As I told you before, if you define your variable as an out, it has to be filled inside the function. But no worries, we're gonna do it right away. And I will go up and immediately add Rhino input and Rhino input custom, because we will probably use some input. We will use some input methods, and that's where they are usually, so just not to go back again. So you can actually go to our point selector if you want at this moment and kind of copy all this, and I will go through it quickly and see if there is anything new or not. Let's first figure what this is. We're not returning command result anymore. We can see actually if this is failure. If the selection went wrong, we can simply just return, because it's a void function, and we will move this point declaration up. However, this is not how we do it. We will use our points that we have here, it's the same name conveniently, and we will instantiate a new point 3D list object. And you see how this disappeared here now, because now we actually created a new array here and the compiler is satisfied. What we will want to do now is enter a loop, and in the same way we will just simply add the location of the point, as I told you before, because this is the property of this class that will actually give you a 3D point, which is what we have here, an array of 3D points. Very good. This is the simple function that selects and returns points, and you have your code in the description, so you can actually use it or pause the video and check it out in slowly if you don't understand anything. But as you saw, I just copied the select points code that we already had before. Notice that we passed our message here, which means I can actually set the command prompt with this particular message. So when you call your function, you can write whatever you want. And now that we have our function, why don't we just test it before we continue? Let's just print out the number of selected points, just to be sure we did it right. We will go to our command that doesn't exist yet. So before we go to it, let's create one, and let's call it x create curve from points. And then in our command we can simply access our useful functions and access our select points. And the beautiful thing is that from now on, whenever you want the user to select points, you won't need to copy paste all the code. You will just write this one single line, and this is that exponential growth of your library and exponential speed of programming that I was talking about. You can type whatever message you want to. Let's say select points to make a curve, and we passed something else. We passed an out point 3D list called points. Of course, a couple of adjustments here. First, the point 3D list is not recognized. Let's go to some of our other commands and copy all of these namespaces, since we are creating so many commands. And you can see you can have an inline declaration, you don't actually have to put this outside of your function. It's interesting, but it will work. You can, if you want to, you can put this here and just call it like this. You could do that, but just for fun and for trying out different things, let's do it like this. And now you can write the line and you can say the user selected this the user selected this many points, not many, come on man, the user selected these points successfully, and hope that the spelling of successfully is right. We will access our points, we will access the count, and we will convert it to string just to be nice. Test this command. I will speed this up just to show you that it works, including the reinstallation of the plugin because we have a new command. I will draw some points and remind you again that the order of points will be important in this case because we will be creating a curve through the points. So if you select all points at once, they will be saved in the array in the order they are drawn. However, if you select them one by one, then that will be the order in which they will be saved. For us, the second option will be better now, and we'll see why in a moment. But let's test create curve from points function command, and you will see it says the user selected 6 points successfully. Great. This means that our one line select point function now works, and you can use it over again throughout the entire course. Now let's create another function now. It's getting serious now. I forgot to comment this. Put 3 slashes, comment whatever you want. This function selects points. Let's copy this, paste it down, delete everything inside, and say this function will create a curve from points. A very interesting function, and let's call it create, or not create, just curve from points. What we want to pass this time is we will pass a list of points through which we want to create a curve, and we will pass a Rhino document. It's not necessary, but we will want to actually draw a curve inside this function, so that's why I will pass it. What we will do is we will create a Nurbs curve, and for that we will use a object type, a class called Nurbs curve, and we will create a new one. We will not actually instantiate it with a new, but we will call the method called create, and we will pass it some arguments. These are some mathematically specific arguments that we do not have to go into now. We will pass it false for being periodic. We will pass the degree of the curve. The most common degree is 3 when it's used in Rhino. If you want to know more about the degree, you have to learn more about the Nurbs mathematics, so check it out online. I will leave some links in the descriptions, or check my lessons on Nurbs geometry if they're out already, if they're published. And if you want to know what the first argument is about, you can see what the help file says, for example. Like here, it says that if it's true, create a periodic uniform curve. If false, create a clamped uniform curve. So without going into mathematics, let's say that what you want is a clamped curve most of the time in order to create a normal Nurbs curve, with the points that you selected becoming control points and so on. You can research a bit on your own about the difference between periodic and clamped curves if you're interested. But let's just say again that clamped curves are usually open curves. So for closed one, you might want to experiment with periodic option because it might give you better results. But as I said, this is a little bit out of the scope of this course. Now, sometimes you will want your curve to pass through the points. Actually, you will want this most of the time when you create them in the code. So there is a method for doing that, and it is also a static member like this create one, but it belongs to the curve class instead of the Nurbs curve class. But since Nurbs curve is inherited from the curve class, as you can see here, then there is no problem. So let's make our function interesting in that manner. So let's comment this out for a second, and let's add another parameter to our function that's called through. So if the user passes true for through, then we will create a Nurbs curve through the points and if they pass false, we will use the points as control points. That's very, very useful. So let's see how to use it inside the function. So if true, we'll do something, which will be create a curve through control true points. Otherwise, use points as control points. Let's say it like that. Doesn't really matter, you can write whatever you want. And now I will not use this Nurbs curve create that I showed you before. I could have used it, and you can experiment with it. It would be a nice exercise. There was another parameter missing. Exactly, it's the points. So if we added these points, theoretically this would be all you need to create a Nurbs curve. But we will here we will use this other method that I told you. We will create a new curve by using the static method called create interpolated curve. We will pass it our point array and the degree, which I told you 3 is the most usual. We will simply then check if the curve is not null, and we will check if the curve is valid. You will see that most objects have this isValid function that kind of checks it mathematical and geometrical properties and see if everything is okay with it. So if the curve, actually it's not a method, it's a property. So if everything is okay with our curve, we will simply add it to our document. Add curve, nice. And you don't want to forget to redraw the views. And if we want to create a curve by using this as control points, then we will create a Nurbs curve like we did here, and then we can simply copy and paste this because we want to do the same check. Now I could use a little bit of polymorphism here and a bit more complicated methods to get this outside of the if, to get this part outside of the if statement and just create a new curve using these methods. But I don't want to complicate that for you now. I don't want to confuse you, so I'm keeping everything separated like this. Once you get more experienced and have more practice, you will start to understand how some obvious code repetition like here can be optimized, how it can be taken out of the if statement, then a new curve created here, and then solved. Now let's just simply go to our command, our new command that will create curves. We don't need to write down how many points we selected. It's not relevant. We will go to our useful function and we will call our curve from points. We will pass it our newly selected points. We will pass it our Rhino document, and let's say we want to create our curve through our points. What you can do here is you can check if your points exists. If the point count is smaller than 1, for example, you do not want to continue with your function. Why would you? Result failure. And if you continue, you can draw your points. And before we continue, let's test it. Again, I will speed this up. So I will simply draw some points in the right order. I will call my curve create from points, select them because I drew them in the right order, and you will see the curve was created through the points. So let's continue in the next video. As I told you before, a curve is a very broad and general term in Rhino and generally in CAD software. A curve can be a Nurbs curve, a line, a polyline, but also a circle or an arc. Even a polycurve, which is a term for a joint curve, is one. Now, I'm not going to go into mathematics here, but a circle and an arc can be approximated with Nurbs geometry. But more often, we would like them to be defined in a mathematically simpler way that we learned in high school. That is why Rhino provides you with the circle and arc structure and also arc curve class that you can treat with the standard Nurbs curve algorithms, work with parameters, domains, etc. So I would be remiss not to mention them because in digital programming, circles and arcs are used a lot, especially in architecture because very often you can approximate freeform curves with arcs, and that often means a lot for the production purposes. Many of the production processes involve bending, and bending glass, for example, or steel is done over cylinders or cones, so you would want to use arcs when you're designing them. So because this lesson might seem to be a bit dry, I will teach you how to generate random numbers, which you will find very useful in different occasions. So there is not so much philosophy behind it. We learned how to make functions really fast, so let's make two more functions, one for drawing a circle and one for drawing an arc. And then we will shortly make curves from them and see how we can use that. So let's do this very, very fastly. Let's copy this thing once. Let's do it twice. Let's do it at once. This function will draw a circle, a single circle, let's say. We will use it later, and we will call it xDraw circle. And what we will pass is a point 3D center. We will pass it a radius, of course, and we will pass it the document. So let's quickly write down what we are doing. It's exactly the same as before. We are using the circle class. We are creating a new circle. And surprise, surprise, there is a constructor that takes the center point and the radius in order to create it. Very simple. We are not closing it. We will simply check if it's valid. We're not going to be able to check if it's null in this case because this is a structure, not a class. Remember, if you don't remember the difference between structure and classes, check it out online or in my courses, basic courses. Structure is a bit simpler version than classes. And we will simply add our circle, and believe it or not, there is a method that's actually called add circle. They made it for every single type of geometry. And what we will want to do maybe now is actually copy this again here, because it's much closer to what we want to do. And we will want to create an arc from points. We will not draw a circle, we will draw an arc. And there are different ways of creating an arc, of course. But let's say we want to create it from 3 points. So we will have point 0, because that's very often how you probably draw it in Rhino when you're creating an arc. You're creating it from 3 points. Or at least I do it. We will just need these 3 points and the Rhino document. And again, not a big surprise that there is an arc class. We create a new one, and not a big surprise that there is a constructor that actually takes 3 points to create an arc. We'll call it an arc. We will check if it's valid and draw it, and that's it. You see, in 1-2 minutes we created 2 functions that will draw a circle and an arc for us, and we will pass it some parameters. So now, just to be pedantic, we will create a new command, just to be a little bit organized. Let's create one, and let's call it create arcs, because circles could be seen as 360 degrees arcs. And let's simply draw a circle and an arc just to see if it works. And now comes the beauty. First, copy all the usings from the class before, and what you can do now is simply copy this one single line. You see how we are speeding up now. Now the user can select the points. They will be saved here. Just to test our command, let's say to make an arc and circles. Let's do this. We can test if our point count is exactly 3. Let's imagine that we want the user to select exactly 3 points. What you could do is actually pass that as an argument here, and then inside this function, go to definition. Remember here, you can pass it, you can make an overload of this function. If you still don't know what an overload is, I will talk about it later. If you want to advance and go ahead a bit, check it out online or in my courses. You can make an overload of this function that passes an argument of the maximum number of points to select, and then you can pass that number here. You will learn how to use all of these little tools once you become experienced. But now let's imagine that you don't have that, as you don't, and let's check if the user selected exactly 3 points. If they did, we will just call our draw arc, and we will pass those points, point 0. We can safely access the elements 0, 1 and 2 now, because we checked and we know that there is exactly 3 elements in this array, and we will pass the document. And why not use this function to create a small circle at every of these points, right? Let's do it like this. And we will give it a radius of 10 and pass the doc. Just as a small example, just to test if our command works, and we will continue and change this to do something else. I will skip this, do very fastly, reinstall the plugin, test the command just to show you that it works. We have exactly 3 points, and we will call our create arcs command, select them, and as you will see, we created an arc through the 3 points and a circle with a radius of 10 around every point. Great. Now what we want to do is we want to randomize stuff a little bit. I will comment this thing out. We will not use this. We will use some cooler application. And I'm not going to explain every single detail of how to use random numbers, but when it comes to generating them, it's a huge subject in programming, in the development in general. So it will work, and if you want to know exactly how it works, you will have to invest some time yourself in analyzing it and thinking about it. If you want to generate any random number, that's relatively easy. In C# we can just use the random class. So let's create circles with random radiuses between 0 and 10 meters for all the points that the user selected. Okay, so we can use the random class, create an object, let's call it random, RND, and instantiate it. And I will write this down and explain what is happening here. I will iterate through our points. And for every point, I will call our random object and its method. Sorry, there it is, random object, and its method called next double. What this will do is simply give me a random number between 0 and 1. As you can see in the description, that is what it does. I will want to save this random number in a double variable. Let's call it random number. And I will want to multiply it, because I don't want to create circles that have the radius between 0 and 1 meter. I want circles that have the radius between 1 and 10. So I will just multiply this number, and this is exactly what will happen. Then I can simply call my useful functions and call my draw circle function, and I will pass it a center point, which will be the current point I'm dealing with, and now I will pass it my random number as a radius and pass the document so I can draw it. So let's test it. Now I will put a fairly large amount of points here. I will copy this like this. Let's see how many points we have. 104 points. Okay, because I want to show you something. If we press create, create arcs, and select our points, you will see our circles getting generated. Now this was fairly slow. If you think it's fast, cool, but in the sense of programming terms, this was very, very slow. I mean, you should have thousands of points, and this should be created in an instant, immediately. The reason why it was slow, let me select all the curves and delete them, and then copy these points again and repeat the command just so that I can make my point. The reason why this is slow, and you can see them being created like this, and by the way, you can see it works. All those circles are created with random radiuses between 0 and 10 meters. The reason is that if you go to our draw circle definition, you will see that we are redrawing our view after every circle is created. What you might want to do is then comment this out as an exercise. Of course, I cannot change my code. I would have to stop the debugging. You might want to comment this out or delete it and then go to your command and actually redraw here after everything is done. And you will see that everything will be then created in an instant, but I will leave that for you as an exercise. At this point, I want to anticipate what you might be thinking. You might be thinking, are you kidding me? All this code and lessons to do something I can do in Grasshopper with a couple of components? Well, I will remind you of what I already said in the introductory video. I will literally repeat it because it's important. If you know how to program in C#, you will be able to do 10 times more stuff than you can do in Grasshopper. For the sake of exercise, I'm programming the methods that already exist in Rhino or Grasshopper, but once you learn how to use this, you will know how to create methods that do not exist there. That's the whole point of programming. You will also be able to use C# to expand Grasshopper components and create new ones, so using both at the same time might be the best solution for you. Whatever you program in C#, especially if you do something in an iterative manner, something that works in loops like optimization, that will work much faster than in Grasshopper, because whatever you do in Grasshopper, it has to be translated before it gets executed. In Grasshopper, the complexity grows exponentially, very quickly. When you program, you can organize your code in different files, classes, functions, and have an overview. Graphical programming can get very, very confusing very fast. What else? With Grasshopper, you cannot make an actual plugin, something that is neatly packed and works on its own. And you have to realize that making your own functions is like making your own Grasshopper components in a way. Once you have written them, you can use them in a single line, like the point selection function we already did. You have it now. Wherever in your code you need to select points, you can do it in a single line. And this kind of efficiency will grow exponentially as you learn more and program more. Okay, let's move to surfaces and polysurface. So as I said, creating courses for C++ and C# are different. So with C++ I kind of stopped here, but since in C# the functions for creating breps are so simple, like these ones, I wanted to show you that you can use this as a template just to expand on a lot of different versions, on a lot of different methods that brep have. And another one, as you can imagine, all these surface creation options in Rhino, like loft and sweep and other, they all have methods that you can call to do exactly the same thing. And just to show you, I will help you loft some curves so that you can see it's the same principle, and then you can apply it to others. So create brep from, let's say, loft curves, and let's pass the Rhino document. Actually, we might not need it, so let's leave it for now. And again, embarrassed that it's so simple, but you can create from loft. There it is. What you will pass now is the array of curves, and you will have to pass a couple of other things. As you can see here in the description, it says optional starting point of the loft is the second parameter, but you can use point 3D unset if you do not want to include a starting point. In this case, let us not include a starting point, so we will put one that is unset. And we do not want an end point, so we will also unset one. And there is, of course, if you know, when you use loft in Rhino, you can choose different types of loft, and there is an enumeration for that called loft type. And if you remember, in Rhino, you can just go now and select a couple of curves and loft them, and you will see that you will have an option to make a loose, normal, straight loft, and so on. You can code all of that here. You can put a normal one, and you can put if you want a closed loft or not. So everything that you can set basically in Rhino when you are making curves, you can do here as well. What is the return type? It's a brep array again, because a loft can result in multiple arrays. So it is in a brep array here. And we can use our same create brep command. And simply, if you want to do it just for the exercise sake, I will comment this out. I will copy this code here, and instead of useful functions create brep from planar or edge curves, I will call our function now that does it from loft curves. And what are we passing? We are passing only the curves, exactly. We are not using the document. And we have our array, we go through the array and we draw it, and of course we can redraw everything at the end. So you see, this is a simple template how you can continue and create breps in many other ways using sweep 1, sweep 2 and so on. So let me create a straight line, then let me create a bit of a freeform line, then another freeform line, and let me move this one vertically. And now start our create breps command, select those lines, and voila, I created a loft through those lines with this, where is my useful function, with these parameters here. And playing with those parameters, of course, you can get different results. So let's continue. I showed you some basic functions for creating breps. There are many others that you can find in Rhino SDK file, and you can find the same logic that we applied here to make them work. So you can take on the challenge and make them work, or wait for the next level course where I will definitely cover some more complicated methods. As I explained to you before, surfaces and polysurfaces are represented with a very neat and powerful class called brep. Now, creating a brep from scratch in code is very complicated. I never needed to do something like that, and hopefully neither will you. When you model a surface in Rhino, you have many different ways to do that. You can create a surface from planar curves, from 3 or 4 edge curves. You can use cross sections with loft. You can use sweep 1 rail, sweep 2 rails, etc. And guess what? For all those methods, there is an underlying function that you can use in your C++ and C# code. We will not go through all of them. Some of them I will leave for the higher level courses, and some of them you might explore on your own, because it will be very intuitive after we finish this video. But here I will cover 2 basic ones, 2 that you will use most of the time, that I use most of the time. We will learn how to create a surface from planar curves and how to create a surface from edge curves. And I will add a bonus here because I'm very nice, and I will teach you how to automatically join surfaces and create polysurfaces. So let's create 2 new functions. You're pretty proficient at it by now, I assume. You can write it from scratch or just copy paste the code. I find copy pasting much more expedient. And let's say this function will create a brep from planar curves. We will call it x create brep from planar curves. And just as a side note, I started naming my functions with an x as well, which is not really necessary. I was naming commands with an x because it made sense, because then you can differ them from other Rhino commands. And for the functions, it doesn't really make much sense, but you can go along with it, or you can, of course, for every of these functions, create your own name. So we'll create brep from planar curves, and we will simply pass some curves as a curve list and our Rhino document. And we won't need anything else. Let's delete everything that's here for now. And let's immediately create another function, because we will use both of them. What we will want to do is create a surface from planar curves, and we will want to create some surface from edge curves with the same parameters. Notice again that the function is static, so we call it without creating an object of the class. Notice that the function is returning void, for example. We will change that, and we will return just a simple brep array, a normal C# array, not a list, a dynamic list, not a Rhino list, not a specialized array. This is a simple array which you will not be able to expand it dynamically, but you won't need to do it because you will see there will be functions inside that will do that for you. The reason why we're returning an array is because we might have several closed planar curves, so we can actually get several breps as an array, and in this other case, edge curves, an array makes no sense, so I will just return a single brep. Now, my C++ course and my C# course differ greatly. In C++, I actually explain smaller amount of methods because there I would have to write again 10-15 lines maybe here just to create a brep from planar curves, but here you're in luck because what you can do is simply call the brep static function called create planar breps, and you can actually pass it the curve array. And what you need to pass it as well is some kind of tolerance. You can literally type in 0.001 or some mathematical tolerance that you want to use for these Nurbs operations, but the best practice is to access the document, and you can access the model absolute tolerance. It's the tolerance when you go to Rhino, Tools, Options, and to Units, you will see the tolerance value there, and whichever values is put inside the document that you're currently working on, that will be the value read here. And believe it or not, this will be enough, except that this method will return a brep array, exactly what we need here, so we will just return the result of this function. Now this is a bit stupid to have your own method that just has only one line inside, so instead of calling your own method you could have called this one, but it works for now, and I just did it to make the point. But in practice you don't have to create your own method, you could literally simply just write this one line. And in the case of our method, you can actually add some more arguments, expand it, so sometimes it makes sense to start like this and continue. With the edge curves we will only want to return a single brep. It will look like this, and surprise surprise, again there will be a brep function that does that for us, a brep method that does that for us, called create edge surface, and we will pass our curves, and that will be it. Now let us create a new command. Let's call it create breps. Delete this. We will of course add the namespaces. I just copy paste all of them. Probably don't need them all, but it's easier. And this time, just to change something, we will not draw the brep inside the function. As you saw, I did pass it the Rhino document. In this case it will probably not be needed, and we can actually delete it. And in this case I will leave it because we will access the document just to read the tolerance from it. What we want to do is select some curves here, and what you could do is you could go to your curve selector and just copy paste this code there like we did before. And I would suggest something else. I would suggest to create a function that actually selects curves in the same way we created a function that selects points, and then we can use it in one line. So why don't you do that? And I will skip over to when I'm done with it. You can copy because there's nothing new there. I don't want to go through it with you. The code will just simply appear here, and you can copy paste it, or even better, make it on your own and see if it's the same. So we jumped here. I created this select curves function that you can create on your own. I simply went to our curve selector command and just copied it here and deleted what I didn't need. And as you see, as a parameter, I have an out curve list that I will fill in here with our selected curves. And as before with our points, I will just put some message that I can pass, and I will put this message in the command prompt. So nothing new here. You already should know how to do this. If not, pause and check out the code and examine it again. And you see I put a Boolean variable in so that I can know if something went wrong. I can return false and then read that if I need it. Now we will go to our new command that is called xCreateBreps, and I will use this simple one line to select our points in the same way I used it before xSelectPoints. I will now use xSelectCurves. I will pass it some message that will say select curves for brep creation. And then I will just simply pass a new curve list. As you saw before, it works like this in one line. I could have taken this outside, but I don't have to. And now we actually have our curves. Now let's do it like this. For example, we can test if the number of curves selected is bigger than 3, or larger or equal than 3, and if the number of curves is smaller or equal than 4. In other words, we're testing if the number of curves equals 3 or equals 4. I could have written this, and it would be exactly the same, and I leave it to you to think about it and figure out why this is the same as this. If you understand that, then you basically understand how the logical operators work. But I will say now, if my curve count is larger than or equal than 3 and at the same time is larger than or equal than 4, which means if my curve count is 3 or 4, then I will create a brep from edge curves. Let's say I imagine my command to do this thing, because in order to create a brep from edge curves, you actually need exactly 3 or exactly 4 curves, otherwise it will not work. So I will call my useful functions and create a brep from edge curves, and I will pass it my curves array, and we do not need anything else. If my brep is not null, if it's referencing something, and if my brep is valid, then I will just add it to my document. And that's it. Now, if my curve count is not 3 or 4, and now I am assuming something, I'm assuming that my curves are planar. If your curves are not planar, of course, creating a brep from planar curves will not work, and you will have to handle these exceptions. But as I said, I'm not going to complicate every example in order not to confuse you. We're explaining now the basics. So I am assuming that the curves here will be planar. In this case, if you have 3 or 4 curves, they don't have to be planar. Creating a brep from edge curves, as you probably know from Rhino, can create a surface from any connected 3 or 4 curves. But as I said, we will assume this here, but in the future when you program something like this, you will have to throw in some functions that actually check if everything is alright, or if everything is as you need it. We will create a brep array, as we know that is our function returns. That is what our function returns, that here it is, create brep from planar curves. We pass it our array, and we pass the Rhino document, and that's it. Of course, now we have an array of breps. We have to iterate through them. Since it is a standard array, we will not find the count that you can find in lists. You will find another property that's here. I just showed you. It's called length. You will have to be careful what type of arrays, of course, you use. With this standard one, again, you will use length, but this will come with experience. And when you iterate through them, again, you will simply check for every single breps, iterator I. We don't want it to be null, and we do not want it to be invalid. So if it's okay, you will just add it to the document. And that's it. So this is how you will create breps. So let's just build this and test quickly. Again, I will speed this up. I will reinstall the plugin and draw some curves and then execute our command. So what I did here is now basically drew a couple of lines that are planar, and there is 1, 2, 3, 4, 5, 6 of them, so more than 4. And I created here 4 edge curves, and as I told you, they do not have to be planar, but they have to be closed, otherwise your functions will not work. And I will start my command called create breps, right? We're mixing some creator and create commands, but that doesn't matter. The naming is really not important at this moment. I will select 4 curves, press enter, and you will see Rhino will recognize. If you want to check if that's true, you can put some Rhino right line here, just so that you can acknowledge that it recognized that you created brep from edge curves, or even inside this function you can write Rhino app right line. I created an edge curves. As I told you, this writing lines is a very good debugging method. And if I execute my command again, create breps, and select this time more than 4 curves, it will execute the second command, which is this one, and it will create planar curves. Now you can really play a lot with these and expand these methods, but I will not go through it all because it would take too much time, and I think you understand the basics now, but I will give you a little bonus in the next video. As I said, this will be a short bonus video where I will show you how to join breps. This can be sometimes pretty helpful because, as you know, in Rhino and generally in CAD software, there is not such a thing as a true solid. If you take a box, you have 6 surfaces connected together. A box is then just a closed poly surface. But let's say if you want to have steel elements on the construction site and then you want to export them into AutoCAD or some other program that read them as a solid, you have to export a closed poly surface. And that's why it is useful to automate joining them. I come from a C++ world where joining is a bit more complicated, and you can see that in my C++ lessons. But since .NET framework simplifies most of the programming in C++, that's the case here as well. Here's what we will do. We will make a function that takes breps in and gives the join breps back. And then we can use that function in our brep selector command. So let us see first what kind of data are we working with. In our brep selector, let's go to our brep selector. You saw that we were working with a Rhino list breps. Okay, interesting, we can acknowledge that. Now let us find the join method. Let's go to our help. In the Rhino geometry, find our brep class and see what we have. So we have here, let's go to methods. What we have here is a lot of methods, and there is one that's called join. Let's see what it does. We can see that we can pass it another brep, and you can realize that this function is basically joining 2 breps. You pass another brep to this one and it will join them. That's nice, but it's not ideal. What we want is to join multiple breps together. So this join breps kind of looks like it's doing the job because it's a static function and it returns a brep array. And the description kind of fits. So this is exactly what we need. Why are we returning an array? Again, you might ask, if we are joining different breps into a single one. Again, you do not necessarily have to have only one as an output. If you imagine the 3 breps are connected in one spot, 5 in another, and you select all of them, the result will be 2 different breps. If IEnumerable confuses you, that is an interface in C# used for collections of data because it supports iteration. And if you do not understand what an interface is, of course, again, check it online or in my C# basics lessons where I explain that. But you also have an option to take it for granted and not think about it for now, especially at this level. Just read it as a brep array here. So let us not make a separate function now, because again this function would probably be a one-liner and we don't need to do this. Instead, let us go to our brep selector where we already have a list of breps, and at the very end, after we are writing all this information, we can use our newly found join function to join our breps. So we know that this function returns a brep array. We will use the angle brackets for that. sorry, not breps, brep array. Let's call it joined breps. And we will call the static function of the brep class called join breps. As we saw in the functions and in the help file, we will simply pass a list to it, an enumerable list, and our Rhino list fits to that because it does implement that interface. And we will need the tolerance. Again, we can use the model tolerance from our document. And believe it or not, this is all the breps that we selected when we executed this command will be joined and exported as a brep array. So what we need to do is what we did many times so far. Let me just check. Yes, we have our I here, so I don't need to declare it again. I is 0. We will go to all our joined breps. And again, I almost forgot, we don't have a count because it's a standard array. We have a length. And we will simply draw them. I will not even do all the necessary checks now. You can do them on your own. Joined breps, iterator I, and that is all. Let's redraw. Now I will open a Rhino file and I will prepare some surfaces for you, so we will jump right there. Okay, so now here I just basically took one simple planar surface and I copied it several times, and I intentionally made them into groups like this so that the end result is an actual array. An end result should be 3 poly surfaces. Later I will also show you how to automatically create your own layers, but now if you want your joined breps to be drawn in a different layer, you just have to make a different layer be current at this moment, and whatever is drawn at the moment will be drawn inside this layer. The add method of the object class will always do it inside the layer that is marked as current. So now you can start your brep selector, because that is where we put our code. We can select this, and as you will see now, you can even hide the first layer and you will have these 3 poly surfaces. So our join brep function worked. If you click on one of them, you will see it's an open poly surface. That's interesting. If you put a box inside your model, and let's put this one, let's change it property, put it in our first layer, the default one, and let us explode it into 6 surfaces. So now we have 6 separate surfaces. Now let's go into some other layer and execute our command again, brep selector. Now all these surfaces were joined again, and this time it's not an open poly surface, it's a closed solid surface. As I said, in practice you will see that the condition will very often have to be a closed poly surface, especially in architecture with some steel elements. You will very often have to have closed poly surfaces so you can export them as solids into other software. So in this way, by using the join brep function, you will be able to easily create solid closed surfaces. There's a lot of stuff you can do with breps. You can trim them, split them, etc, etc. For most of those methods you can just follow the logic that I hope you understood by now. But you can always go to the higher level courses that I will make, where I will deal with those more complex methods. Let's now go to meshes. We covered almost all basic geometrical types of objects, and we need to cover meshes. As I told you before, Rhino is a Nurbs modeler oriented toward Nurbs surfaces and Nurbs curves, but you cannot avoid the mesh. Mesh is everywhere in computational geometry, and even those Nurbs surfaces can be meshed, and have to be meshed actually, so that they can be rendered on your screen. Nurbs is a mathematical representation. It's infinite in detail, but for real-world purposes we need finite, discrete representations of geometry. And the mesh is the simplest and most ubiquitous way of representing 3D geometry. Now, when working with meshes, you do not usually create them from scratch, but I think that that is the fastest way of learning about them. So what we will do here is twofold. We will create a function that creates a simple mesh from scratch. This will make you understand how simple the mesh structure actually is, and it will inspire you to think about ways in which you can explore this. And I will show you how to take a brep as an input and automatically mesh it. And as far as mesh properties go, I will show you briefly how to access different parts of the mesh, like its vertices or faces. And later on you can use them to generate different things. So let us create a command that creates a small random mesh. And let's call it xCreateMesh. Copy all the namespaces. Now let me show you what kind of simple mesh we will make. It will look something like pizza from the top. I think I saved the file here. It will look exactly like this, something like the pizza from the top, but what I will do is I will raise the middle point here so that we just have this kind of a simple pyramid mesh with what's here, 8 sides. And I drew it already in Rhino because I will actually use the existing point coordinates, so we can create the geometry from scratch. And in order for it to be easy, let us put this middle point, let's move this to 0, 0, 0, and then move this vertically from here to here, just so that we have some symmetry among points and that you will see that it will go easier. Now we will use this mesh creation for different purposes, so let's just create a function that does that for us. Since this command that we just created, create mesh, we will use it for different purposes, and I don't want to put all the code in here. Let us create a separate function so that we can just put one line there. Let's find one short function, short method, so we can just copy it. And let's say this method will, or this function will create a mesh pyramid. And let's call it like that. Let's call it xCreateMesh pyramid. Again, no reason to start these methods with an x, but I already did it, so let's continue like this. This function will return a mesh class, mesh type. We will create one right away so that we can know what we are dealing with. Forgot the equal sign. And we will turn this mesh, which at this exact point is empty, doesn't have anything. And then what we will do, we will simply add some vertices and some faces to this mesh. What are vertices? Vertices are just points with their coordinates. And keep in mind that every point will have its position in the vertices array, its index, and this index will be used to define them, as you will see. So what you can do now is you can set vertices, you can add a new one, and you can simply write the coordinates. So why don't we evaluate this point and copy these coordinates of this point here. That will be our first point. Let's mark it as the center point. And this vertex, because it's the first one we added, it will have the position 0. Now let's continue and add all other points starting from anywhere. I can start from here, and I'm gonna skip now to where I actually inserted all of their coordinates, and you can do the same. Okay, so what I did, I just simply read the point coordinates here. I assume this will be my point 0, and then I started here. This will be 1, 2, 3, 4, 5, 6, 7, 8. And I indexed those points here just so that you know what we're talking about. And the coordinates are very similar because of the symmetry of our drawing. We created a mesh and a mesh has vertices now, but if you listen to my videos where I explain meshes, including this video where I explain the difference between Nurbs and mesh geometry, then you know that a mesh also needs faces. So let's create some faces and we will define each face. We will add face, we will define it by telling it which points actually define it. So in our case, if you remember, this is our point 0 with the index 0, and then this is 1, and then this is 2. So this first face is 0, 1, 2. The next is 0, 0, 2, 3, 0, 3, 4, and so on. This will be our faces. So I will jump again. And now I simply added some faces. I didn't add anything on the bottom, I just simply added all these triangular faces, but in the same way you can add quadrangular faces by putting 4 vertices here in this array. You can test this if you want. Once you're done, you can add an additional face. Let's say if this is our point 1, this is 2 and 3, 4, 5, 6, 7. We can add a quad face that goes 2, 3, 6, 7, right? Let's say mesh, faces, add face, 2, 3, 6, 7. And we will see how that goes. For now, this mesh, because it doesn't have a bottom, will not be closed. And it's, of course, later on you might want to create closed meshes, but that's outside the scope of this particular video. There's a couple of more things I want to say here. Every mesh has an orientation, a normal. So if you're rendering something, you know that every face has a certain normal, and you know that sometimes the mesh faces are not oriented properly and you have black faces. If you have those black faces, sometimes you can save that with a two-sided material and so on. But how is the orientation of a mesh face determined? Well, simply by the order of points it's defined with. So if it's going in a clockwise, if the vertices go in a clockwise order or a counterclockwise order, that would determine the orientation of this face. So this particular face here, if it was not 0, 1, 2, but if it was 0, 2, 1, so from here, here, then its orientation would be different. If you use a 3D face command to draw a simple mesh face in Rhino, like this, you can use the command dir, which will show you the direction of the face. And if you draw it in a counterclockwise order or a clockwise order, you will see that its orientation will change. This is important, of course, if you want your faces to be oriented properly, but as I said and as you will see, you will rarely create meshes like this from scratch. Now we have to finish up our function. We will have to call our methods, make the mesh robust and nice. We will call the method compute normals, and we will access first its normal properties, and then we will compute the normals, which will do the recalculation for us. We can call a method compact to just remove anything that's unnecessary. It's just a simple cleanup. And if the mesh is not null, we can return our mesh. Otherwise, we can return null. Null reference, meaning that our return mesh variable will not reference anything. And we can simply delete this now because we have covered the return. I forgot the semicolon here. Okay, we computed the normals of the faces because a mesh needs its array of normals, and we made it compact. You can read again in the help file why it is useful to clean up the mesh. Good. So now let's see what we get. We'll go to our create mesh command, and we can simply call our useful function that creates the mesh pyramid. We do not give it any arguments. We created everything. Or no, sorry. We do not give it any arguments. I copied this, that's why it remained, but we really do not need a curve list as an argument. I hope you caught this on early on and then corrected yourself. If not, you can do it now. As you see, this is our mesh, and if our function returns something, we can add object to our document. So let's see if I made some mistakes. I will execute our create mesh command. And as you can see, I did screw up some coordinates apparently here. But all in all, aside from this simple face that is missing here, it's a normal mesh. Let me just see from the top view which coordinates did I screw up. So it's the 1, 2, 3, 4, 5, 6, 7 and 8. Maybe it's just the faces. Yes, it's just the faces. I didn't screw up anything actually. I just forgot to add some faces. What we will need here is another face from 6 to 7 and then another one from 7 to 8 and another one from 8 to 1. Very important, you want to close with the last one. So let's test this again. I will call my create mesh command and it will draw us our faces. And if you click on our mesh, you will see that it's an open mesh. And if you want, you can try to close this mesh with adding some triangles here. For example, one triangle here, one triangle here, and another here, and another here. And if you actually did that, you should theoretically get a closed mesh as a result. And as with closed solids and closed surfaces, very often what you will want to have is a closed mesh. If some of the faces are not oriented properly, for example this face, you can just change the orientation by changing the number of vertices. So first, as I said, you will almost never create meshes from scratch like this. We're doing it now so you can easily see its structure, that it has vertices, faces, and nothing else, how simple it is. There is another function that will unify all mesh normals for you, and it's called, surprisingly, unify mesh normals. And if you know Rhino, you know that there is a command in Rhino that does the same thing. The command is called unify mesh normals. And these two do the exactly same thing. So sometimes if your mesh doesn't look perfectly, or you can even test it a little bit, you can change the orientation of one of the faces here or two, and then call unified mesh normals and see if your mesh looks properly. Again, no reason for me to make this video 45 minutes long while experimenting with different stuff. You have to do it yourself, you have to exercise it on your own. I'm just trying to show you the basics here and explain to you the basics of the mesh structure and mesh creation. As you saw, a mesh has some of the basic properties like its vertices, faces, normals, and you can access them and change them if you want, and add new ones and so on. If you look at the mesh methods, you will see lots of interesting ones, but the ones in which we will be interested at this moment is how to mesh a brep, because that one will often be very useful. So let's try to do it. You learn how to create a mesh from scratch, but that's not what you will usually do. Sometimes you will mesh a surface and then use that mesh for other purposes. And in most cases you will select an existing mesh and then you will want to access its vertices, meshes, edges, and want to do something with them. I will show you both of those things in this video. So just to realize what we will emulate for a second, you can go to Rhino and draw a sphere. Be careful not to draw a mesh sphere, but just a simple normal sphere, which is a Nurbs version of it. And now simply execute the command mesh. If you select your surface, you will have the option to choose between simple and detailed controls. Let's just go to simple ones for now. You can switch or move the slider toward more polygons to generate a denser mesh, or toward fewer polygons to generate a less precise one. And let's just choose a medium number of polygons and press enter. You will see now that we have a surface and a mesh here. So this is basically a discrete representation of your Nurbs surface. Nurbs surface is extremely precise, mathematical, a continuous representation and mesh is a discrete one. And as you can see, if I delete my surface, I have quadrangular meshes and I also have triangular. I have quadrangular faces and I also have triangular faces here at the top. This object type, a mesh, uses far less memory than its Nurbs counterpart, and that can be easily exported or used for CNC fabrication and so on. So what we will try to do is emulate this process in code for creating a mesh from a BREP. Now why don't we close the Rhino for now and create a new command called mesh BREP. That's it. We delete this. First we will want to select some BREPs for the mesh, and we're not going to select only one, we're going to select more of the BREPs. So what I did, and what you can do on your own if you want to do it as an exercise, I went to our BREP selector and I simply copied this code from the very beginning in order to create a new function in our useful function that's called select BREPs. So we created a function that selects points before, a function that selects curves as well. There it is. And now I just created a one that selects BREPs, and if you compare it to the select curves ones, you can see it's very similar, except that our array, our BREP array, is now saved as a Rhino list. You can also pause here, but you have the code as well, and you can also only copy paste it if you don't want to waste time, but it will be a nice exercise to make it on your own. So now we have a function that will select some BREPs for us, and in our mesh BREP, new mesh BREP function, we can do that. We can create a Rhino list with BREPs. This IntelliSense is again creating small problems because we did not include all the libraries, so he actually doesn't recognize BREP because we were missing Rhino geometry. Now we are recognizing it, and then we will simply call our useful function select BREPs. And if you remember, we can just type select BREPs for meshing, and we could actually declare our variable here. If you remember, we had this case before. It's much easier than to do it outside. It's easier to read. Okay, now that we have our BREP array, let's simply iterate through all of them, and we will mesh them. So, as you would imagine, there is a function, a static function belonging to the mesh class, and you can find it in your help file. If you go to Rhino geometry and then to mesh, you will find its static method called, where is it? It's here, create from BREP, and we will use this one where we are passing the BREP and something that's called meshing parameters, and we will check it in a moment. Let's just write that down. So what we will want is to call our static function. Let's start by calling it create from BREP, and we will not use this this simple version where we're just passing the BREP because I think it's even obsolete. What we will want to do is pass our BREP, and we will want to pass something that's called meshing parameters. So let's comment this out for a second and see what meshing parameters are. We can click here to Rhino geometry, meshing parameter, and it says that it represents settings used for creating a mesh representation of a BREP or a surface. Interesting, that's what we'll need. If you go to Rhino and you execute the mesh command as we did, and you chose the detailed controlled, let me draw our sphere again, and you execute the mesh command, and this time go to the detailed controls, you can see all these settings. You can set the maximum and minimum length of the mesh edges, maximum angle, and so on. And you can do that in code as well. And you will do that, and you could do that using the meshing parameters. So for example, you could write something like this. You could create an object called MP in the standard way of creating objects. And this object is, as you can see in the help file, has a lot of different interesting properties: maximum edge length, minimum edge length, the ones that you basically saw in Rhino. So you could write minimum edge length is 0.1. You could write maximum edge length is 2 for your mesh, and then what you would do is simply call your function and pass these meshing parameters. And your function, if you hover over it, you could see that it returns a mesh array. So you could create a mesh array, and you could just implicitly define it as var, and your compiler will recognize it. So this will theoretically create a series of meshes from a single brep. Again, one brep when meshed can return multiple meshes. That is why for a single brep we get an array of meshes returned. So what you will want to do once you did mesh your project, you will want to enter another nested array in order to draw all your meshes. And let me just for that sake use another option of for called for each, just to test that as well. And I explained this, of course, in my basic lessons. This is just another way of using a for loop. So not with an iterator, but actually writing for each and then defining a new variable. We can call it however we want. We're going to call it mesh for now. So for each mesh in our array meshes that has just been saved here, we will we can add the mesh to the document. But instead of adding a mesh to the document, again I'm going to do something new, and I am going to weld our meshes together. So assuming that our brep is a polysurface or something like that, and this process actually created multiple meshes, what I can do is I can create a welded mesh, and I'm going to do it like this, simply creating a new mesh object. And then you create a welded mesh by adding all meshes together. So every mesh has this method called append. Well, you can simply add multiple meshes together. This is not really welded in the proper sense. It's more like joined, but I will leave you to explore the meshing operations, because this is out of the scope of this lecture for me explaining now what welding of vertices of meshes is, what naked vertices are, and so on and so on. I did call this welded, but I'll just point out to you that it's not a truly welded mesh. It's just a couple of meshes joined together, so to speak. And as I told you, in most of the cases this will only return one mesh if your brep is relatively simple, but in case you have some complicated polysurfaces, the meshing of a single brep might result in multiple meshes, and that is why appending them together you can get one mesh that you can add to your Rhino object then. And before I test this, I will actually not test it with these parameters. I will let you play with them. Again, don't want to go too much in detail. What I will do is I will choose one of the default properties or default settings. If you go to your meshing parameters, you will see that you will find a property called a quality render mesh that you can simply pass, or there is a quality called fast render mesh. So what you can simply do, there are static properties. You can access your parameters meshing parameters, and then you can say quality render mesh. What this does is sets all these values for you for some default quality render mesh appearance. If you want a rougher mesh with bigger faces, larger faces, then you can put a fast render mesh here, and you can experiment with both of these to see what results you get. Sometimes you will just want to use this fast default parameters, sometimes you will want to set this exactly however you want it. And what we can do, we can redraw our views at the end. And I think I prepared a small, let us build this, and I think I prepared a small file for testing. So what I did is I created a simple surface here and created 3 plane surfaces that I connected in one poly surface, just to show you that this will work. I will go to our plugin manager because this is a new command. I will simply reinstall, and we will start our mesh brep command. We can select multiple breps if you remember, and for each one of them we will create a mesh. But you see here, if I hide my poly surface, it's a very simple mesh with 3 faces. Even though I put a quality render mesh, for a very simple 4-corner surface you do not need multiple faces even for a quality rendering. But once you experiment with fast render mesh or with different settings, you will see the differences in this curved type of meshes. And you can see with the quality render mesh, this is as detailed as it gets. If you want to have very detailed discrete faces, then you will want to start playing with this mesh parameter here, for example with a maximum edge length. But this is all very intuitive, and I think I gave you a template of how you can use it. So try it on your own, experiment on your own. You can also experiment with different methods, and if you are having problems with anything, I will always be there to help you. If you meshed some boxes or cones, then you might notice that the mesh will be split in several parts. Well, if you want to handle that, you will have to weld the mesh, but I will let you experiment with those options yourself, or again wait for the higher level course, because I estimate that it makes no sense to go deeper into this subject, because if we digress and branch out like that on every occasion, we would lose the thread, and this would become an all levels course that would most likely confuse you. I want to teach you the basics and point you in the right direction when we are at some crossroad like we are here, so that you can explore it further on your own, or simply wait a bit until you finish the level 1 course and then step up to more complex methods of geometry generation. In the previous section, when I showed you how to select meshes, we already did some projections, changed vertices, read the number of vertices and faces. I think you have enough to go on, and we will talk about some important stuff like how to debug your software if you want to do it properly, how to delete objects from the Rhino document, because that might be as important as creating them sometimes. And we will talk a bit about garbage collection. So let's go. I showed you how to create geometry, that is how to add Rhino objects to the Rhino document, but sometimes you will want to delete those objects, existing ones or the ones you just created. That's not very complicated, and I will show you how to do that in this short video lesson. So since this is very simple, let us not create a new command here, because as I said, it's very trivial, and I will show you how it's done and let you experiment with it. Let's go to our very first command that we made, this PA C#1, where actually the wizard generated this code for us. But you can go into any of your commands where you're actually adding a document to the objects. And if you hover over the add line, you will see that this function actually returns a GUID. And what you could do is you could save that which your function returns in a variable. Let's call it line ID. And once your object is actually drawn, you can access the object table using its ID at some moment later when you want. You can simply access your object table, and you can call a delete method. And what this delete method needs in one of its overloads, as you can see here, is simply an object ID, and you can pass it. We have it now, and it's asking you if you want to do it quietly. You can say true. Quietly just means without any additional messages, or without actually letting you know that the object is deleted. So this is how you can delete it. But I will show you a more comprehensive way, a more logical way that will also help you understand how objects work. If you go to, let's say, if you go to our curve selector, for example, you will see, scroll down a little bit. You can do this wherever you want. You can go to your BREP selector or mesh selector. The point is that once our users selected the objects they need, if you remember, we iterated through them and then simply accessed the curve method. But what does this curve method belong to? If you hover here over the object, you will get that this method will return an object reference. We talked about this a little bit before, but let me talk about it more now. If you're not clear what I'm talking about, you can see that here with our GC, we're dealing with the type getObject. So if you go to your help file and you write getObject, you find that class. Here is some method that will lead us to the class, and you will find its methods. Among its methods you can find our objects method, and you will see that it returns an array of object references. As I mentioned before, it is a class made to reference objects in the Rhino document. So we can use this as well in order to delete objects, and much more than that. For example, if I typed in object reference, and remember, for this, in order to use this object reference, you will actually need to use Rhino doc objects namespace. So I will use my object reference, and I can say it is equal to exactly this. I will just not access the curve method. As you can probably assume, I can now replace this simply with object reference if I want. But the most important thing is now that I have a variable that points to the actual object in the Rhino document. This is important because before we actually drew an object, we actually added it to the document using add line, and that's why we got the GUID of the document. But in our curve selector case, we are not adding the document. We are not adding the object to the document. It already exists. We are just pointing to it. When we selected it, we just point to it using this variable. And afterwards, at some point, at any point where you want, you can access the objects table, and now in the delete, you can pass the object reference. In one of the overloads, as you can see here, you can pass your object reference, and again true in order to delete it quietly. If you just pass false, it will show you a message box showing that you just deleted an object. And a little secret, if you want to replace an object, you do not have to actually delete one and then draw one. You can use the replace method of the objects table. Notice that I'm not testing any of this because it's really trivial and intuitive, and I hope you will test it in any way you find suitable. So whenever you draw an object, you can either use its GUID as you saw before, or you can point to it and use its reference to delete it, and as you can see now, you can use its reference to replace it. And this method is interesting because you can see it has 35 overloads, and it's great because all those overloads are made for different types of geometries. So if you passed a GUID of the object or object reference, so in this case, let's say pass object reference, and now I can replace this object with new different type of object, let's say line 1, and then I can define my line however I want, or with some new curve. And this replace object, as you saw once I opened the bracket, also works with the GUID. So you can choose if you want to do it in that way. So in your original command, you can simply add a line here and then replace this same line by using the GUID, how we did before. You can use the line ID and replace it with some new line that say just reversed from point 1 to point 0. Whatever you want to do. Okay, let's test this for a second, just not to leave you stranded. I will just create fastly 2 points, let's say point 3 and point 4, and give it some wild coordinates. And what you will see is that we will draw this line, and then whatever we draw, it will simply be replaced by this one. I will zoom out a little bit because I don't know which coordinates I exactly put. I will execute our original command, and whatever line I draw, it will be replaced by this weird line that I just defined using these coordinates. Okay, so before we wrap up this section, let's talk a little bit more about debugging. When it comes to debugging, I usually rely on common sense. You program bit a bit, and when your program stops working, you usually know why. Because of the last thing that you changed. Not always, but very often. In C++, there is a lot of crashes while you're working because you have to be careful with pointers and reserving and freeing up memory. In C# we have something that's called garbage collection, which I will explain in the next video and which makes things easier. Very often I will use those write line functions to write where I am in the code and what I get in return. If you get used to doing this and just comment everything out when you're sure everything functions well, that's a very good habit. And you should always check if your objects are valid or maybe empty, like we checked with our curves and our meshes and our breps, if you remember. With all these simple tools, you will not really need any of the standard debugging techniques, but if you do, this is how that works. And again, I will show you this on a very trivial and simple example so that you can understand it and implement it in more complicated ones. We will stick to our original command where we simply draw our line at the end of the function, and let's draw something else. Let's draw a point. Just to have multiple actions, we will add a point, point 0, and then we can add the point 1. And I will show you in a moment why I'm choosing to have different actions. Now in Visual Studio you can set something that's called a breakpoint. So what you could do is right click here and you could find the breakpoint and insert a breakpoint, and this will appear here. You can do the same thing here as well, and let's say here as well. This will make your program stop. When it executes your plugin, it will stop here, it will pause, so you can examine what is happening. You saw that you can also insert something that's called here. You can also insert something that's called a trace point. They will not make your program stop. Instead, they are used to trace or inspect something without actually pausing. But we will not go that deep now. So if you created your points, you can just press play for debug. And you can start your command. And once you selected your 2 points to draw a line, you see the code will pause exactly here before it draws a line and jump back to Visual Studio. Just because you reach your breakpoint. And you can see our variables there, 0.0, 0.1, and you can check their values. For example, here we see the coordinates of our points and they are okay. In some cases, maybe you will get some variable and you can examine if it's actually null here or not, if it holds something in the memory. This will help you realize if something went wrong. What you can do here is simply go on continue, then the function will jump to the next line when you put the breakpoint, and again to the next line. Now nothing is happening between these lines, that's why we have no changes here, but usually you would jump to different functions, to different methods that use different variables, and you might expect what is happening. And after you continue, your function will simply add and just draw this line and these 2 points for you. And I hope you get the gist of how this works. I told you that I will not go deep into debugging because everyone will create their own style of tracking mistakes. But with a debugger you can simply place your breakpoints and delete them afterwards, and then inspect your variables once your program pauses. There you can see if some of your geometry is empty, some array doesn't exist, and you will realize where the problem is. You can do that as well by using WriteLine to track what's happening and always check if everything you need is there. We talked about creating of different types of geometrical objects, points, curves, breps, meshes, but there's a lot more out there. How about creating annotation objects? How about transforming your objects, translating, rotating, scaling? How about creating your own layers automatically and your own classes? We will cover this in the following section, so let's go.